Okay, everyone, I'm Steven, and this is my week 2 presentation. I'm going to start from kind of the middle of my slideshow, so we're just going to go straight to it from the current slide. Again, talking about pseudorandom numbers and presentation 2. So previously, I talked about the while method, where we essentially square some large number, and that large number that we have is our seed number. It's something that we choose, um, and essentially in the while method, we're taking that large number, parsing out the middle of the number, squaring that number, and then that number is some other large number, supposedly random, and then we rearrange the quarters of the number, the middle quarter and the final quarter of the number, and then we resquare the number again and again and again. Um, and it's essentially a rinse and repeat of look at the middle, rearrange the middle, square it, and you have your next number, and you do the iteration again and again and again. But this week, I'm going to talk about linear congruential generators. So it's a little bit different method, um, but like the while method, they generate seemingly random numbers, so more pseudo-random number generation. Um, Instead of using a middle square method, we're going to use a recursion algorithm, um, and hopefully we'll get some pseudo-random numbers. But like the while method, we kind of want to standardize the output of the sequence that we get. So we'll get these large numbers, which is of course good, but we really want to have a useful way to talk about the numbers, and so we want to apply um, some form of standardization and some uniform distribution. So that's typically from 0 to 1 in nearly all cases. So I'll talk about that as well. And here's our recursion formula for linear congruential generators. We have our x sub n plus 1 is equal to a times x of n plus c mod m such that n is greater than or equal to 0. So we have, kind of like before, we have our seed value is going to be n, the n term when n is equal to 0. And then from that term after that, x of 1, x of 2, x of 3, so on and so forth. Our u of n is our scalar that I was talking about, our normalizing, our uniformly generated sequence, where we have our sequence after we are done generating it, and then dividing it by the modular value of m. And so that's how we get uniformity. So like before, we have some sequence of n values, our starting value of x of 0, m is our modulus, a is our multiplier, and c is the increment. U of n is a scalar, like I said, to normalize the sequence to make it between 0 and 1. And a little bit more, so we have these three terms which must be below the modular value m. Generally good choices are a greater than 2 and c greater than 1. We can see on a first glance even a times our series. If a is 0, that's going to cause some trouble because we're essentially saying that every term is c mod m, and we're stuck in that, so there's no pattern. Even if a is equal to 1, it's still the previous value plus our incrementer of c mod 1, and that's not a very good pattern anyways. It's going to be a very short period. Similarly, when c is 1 or 0, then the incrementer is negligible and we have repeating patterns very quickly. So m should be significantly large, a should be greater than 2, c should be greater than 1. And ideally, we want all the values between 0 and our modular m minus 1, to be generated. So if m is 100, we develop all the values 0 to 99 in some order, and that'll be a successful full period length of m. And that's a great success because we have all these numbers. Our period is the full length of m, and it's a successful attempt at making a recursion sequence. So let's just go through a simple example. So I've chosen x of 0 to be, our initial value, our seed value is 0, our a value is 5, our c value is 1, and our n value is 8. So x of 0 is 0, x of 0 gets plugged in, multiplies by 5 plus 1, mod 8 is equal to 1. So 0 plus 1 mod 8 equals 1. Continuing through, we have 1, 6, 7, 4, 5, 2, 3, 0, and back to 1. So we developed the full sequence of 0 through 7 m minus 1 terms in our sequence that we generated. So we successfully generated all 7 terms of our recursion sequence. But similarly, if we have a different equation, a second example, let's see if we can kind of mess it up and see what's going on here. So we've chosen our a value of 3, our c value of 5, and our modular m value of 15 with our initial seed value of 7. So first term 7, 7 goes in, 7 times 3, 21, plus 5 mod 15 is 11. Okay, so 7, 11, and so on and so forth, 8, 14, 2, 11, 8, 14, 2. So we have our first problem here that we can see. And I'm sure that some of you can actually see a couple little hinky things that I've changed from the previous example to this one, just regarding the A, C, M, and X0 values, and we can talk about that a little bit. But we have a period of 4, a period length of 4, when we were looking for a period length of 15. So we've already found a method where we can go ahead and choose A, C, and M all we want, but we really should be specific about the A, C, M values so we don't have these very small, kind of useless periods that'll cycle very, very quickly. We're looking for large modular numbers of M that cycle through the entire values of M minus 1. So let's talk about those restrictions. An LCG, linear congruential generator, produces a sequence x of n of full period length m if and only if the following. C is relatively prime to m. A is congruent to 1 mod p for each prime divisor of p of m, and A is congruent to 1 mod 4 if m is a multiple of 4. So previously, we've got some trouble here. Both 3 and 5 are congruent, are not relatively prime to 15. And so that's kind of an interesting thought. So what do we need to talk about that? Let's go ahead and talk about the proof for the sequence. And it'll be a little bit dense, but let's just go through it. So we want to show how the number xn plus k that has been recursively defined in the recursion equation can be expressed directly by the initial value x sub n and the parameters of m, a, and c. And so this is our assumption of x sub n plus k is congruent to a of k x sub n plus ak minus 1 times c divided by a minus 1, all modulated by the value m for all k greater than or equal to 0. So we're going to do just a quick induction proof. For the case of k is equal to 0, x of n plus 0 is congruent to a of 0 x sub n plus a to the 0 minus 1 times c divided by a minus 1 all mod m. And now I want to consider it for the k plus 1 term. So for the n plus k term of the sequence of the sequence x of n, consider the n plus k plus 1 term. And we'll have, this is just a recall from our previous summation. We want to show it for k plus 1. After showing it for k plus 1, we want to substitute the x sub n plus k value, so our x sub n plus k value, into x sub n plus k plus 1. Gives us the following. After the following, we want to distribute this outside a to the inner terms, a to the k plus 1 times a. This is just pulling a 1 out of a times a minus 1. The c is still there. And again, we want to distribute the a value one more time. But we notice that we have an a minus 1 over a minus 1, and a minus 1, and some variant of a minus 1 here. And so we can simplify that, distribute the a, and simplify to a to the k plus 1 times x sub n plus a to the k minus 1 times c over a minus 1 mod m. This is just previously from before, which is the n plus k. This is the previous our conclusion from before. It's the final statement we have, which is the n plus k plus 1 term of the sequence x sub n. Hence, by induction, our sequence is true for all integers k greater than 0. In addition, setting n equal to 0 gives us x sub k congruent to a of k, x sub 0 plus ak minus 1 times c divided by a minus 1 mod m for k greater than or equal to 0, which gives the congruence that we were looking for. So, good. In the conclusion, thus the subsequence consisting of every kth term of our series is itself a linear congruential sequence with the multiplier a to the k mod m and an increment of a to the k minus 1 times c over a minus 1 mod m. Okay, great. So what does that necessarily mean? Well, let's go through a final example kind of talking about what we really need. We're still going to consider the linear congruential generator with a modulus of m to be some 2 raised to the beta greater than 4 such that beta is the positive integer values. And we want it to produce a full sequence of x sub n with a full period if and only if c is odd and a is congruent to 1 mod 4. So we're still following those 3 criteria so far about m being greater than or equal to 4, but it's some 2 to the beta in this case. And our other criteria of a is congruent to 1 mod 4. So we, again, choose some parameters. What's interesting is our x sub 0 value and our c sub 0 and our c value won't really matter. It kind of matters. It's all on our a value and our n value. But again, we chose our parameters, x sub 0, 7, a, 13, c, 5, and m, 18. Our first term, 7, of x sub 0. Our second term, x1, is 13 times 7 plus 5 is equal to 6, or is congruent to 6 mod 18, x2, so on and so forth. So the sequence we generated is our first term, 6, 11, 14, 7, 6, and there's the repeat right here. So we've developed all the numbers from our value of 0 to our m value of 18, or m minus 1. So our 18 values, 0, 1, 2, 3, 4, 5, 17. And they've appeared in this order that we have here. So our recursion sequence gave us a seemingly pseudo-random output of the numbers 0 to 17 in random order. It's a full period. It's what we're looking for. We didn't violate any rules. Our a value of, or our c value of 5 and our m value of 18 is equal to 1. It's relatively prime. We're still good there. 13 is congruent to 1 mod 2, and 13 is congruent to 1 mod 3, where 2 and 3 are the prime divisors of 18. So we've really satisfied all the 3 principal conditions of our linear equation formula. All right. Thank you very much.